Hello, welcome to the floating tape lab. Here, we're really trying to find out what these two charged tapes that we create in the lab are going to do with these excess pools of electrons on the surface, such as we see here. The purpose of this lab was to conduct an experiment in which the approximate excess charge on a piece of clear tape could be measured. So what we're really looking at here is a point charge model, where we're trying to see here, using a free body diagram, how the electric force and gravitational force act on this upper tape in order to find out the actual charge of each piece of tape. And we can do that through these fundamental principles of physics, where we take a look at the charge of an electron, Coulomb's law, that equation right there, and then also how that translates into a force equation by multiplying the field by another charge. And then we're also looking at the force of gravity near the Earth's surface and the area of an atom, which is 1 angstrom squared. So what we're looking to do here, we see that in the lab the approximate charge of the tapes were found, the number of electrons were found, and the ratio of electrons removed to atoms in the tapes were also found. And some assumptions we're making for the entire lab here is that each piece of tape has the same charge, because they went through the same process, that the center of each piece of tape can be used for calculations, and that just like in the clear plastic pen example, each tape is assumed to have a net excess pool of electrons, making each tape in itself negative. When we actually look at the experiment, we did this in a way that we created two upper tapes by ripping them off of a base tape to give them a surplus pool of electrons. So these were tested by putting our hand near them and making sure that they attracted, and the actual experiment was conducted by raising one negative tape up towards the bottom of another, allowing it to sort of repel each other and push the tape upwards. The distance between these two tape strips when they started to float the top one was recorded, and that was one of the measurements that we used to calculate the actual charge of the tape strips. So here's the system and initial conditions. The system is only the upper tape. That's what we're measuring the effects on, and so that's what we're going to assume is our system for the experiment. Everything else is outside the system. This includes other tape, and includes the stand for the experiment, and everything else in the universe. The initial conditions that we're looking at is that these two neutral pieces of tape were then charged with the base tape and upper tape procedure by ripping one off of the other, and that the initial lower tape has no effect on the upper tape, even though technically from that far distance the electric fields are affecting each other. They're not significant in any way. This is the code that I created for the experiment. We can see on the left we define our constants and then run them through a charge calculation where we find out the mass of the top tape and use it along with Coulomb's the constant K, and we have a representation here, and you can see over at the bottom of the result here we're going through, and it finds that the charge needed for these pieces of tape in order to levitate the other, which happens when the force, the net force is equal to 0, and we can see in later calculations that will equal this charge calculation right here in the middle on line 13. So what we can see here is that exact charge code right here. So as we go through this process right here, we can take the Coulomb's law, F equals mg, and set them equal to each other, because know that the tape is experiencing 0 net force, and we can turn that into this equation here. This discrepancy between code and math doesn't really exist because we based one off of the other. And then we can see as we go through this calculation right here, dividing it by the number of charge, we can find that we ended up with approximately 8.966 times 10 to the 10th electrons. Oh, and that the actual charge of the tape was 1.43 times 10 to the negative 8th coulombs. As we go through these calculations, we can also try to extract how many electrons per atom there were. And we took a couple assumptions that are listed here, and as we go through the calculations, we find out that the ratio of electrons to atoms ended up being 2.135 times 10 to the negative 7, which means that only 1 in every couple million atoms donated a single electron. So as we're looking through our conclusions, we're seeing that just like the pens, each tape possessed extra electrons. The charge of each tape was 1.43 times 10 to the negative 8 coulombs, which is agreed on by the code and the math, and that 8.966 times 10 to the 10th XX electrons were transferred to each tape. And because of the large number of atoms, 4.2 times 10 to the 17th, the ratio of electrons to atoms was this extremely small number. Possible sources of error that we have are possible differences in charges between the tapes because of slightly different preparation methods, and due to the quick nature of the floating, it's possible that the distance between the tapes when floating was measured to be slightly off. It is also due noting that what if electrons and protons switch their charges, nothing would actually happen that's different because the same fundamental differences of charges came into effect. There was nothing that would alter if the masses of the electrons and protons were actually different. And why is it important to handle them as little as possible? That is because anytime anything touches the electrons, it can transfer them to it, which loses charge.